All right, so let's get started. So we'll have our midterm next week, so at the same time, and it will be a closed book midterm exam, and the coverage will be from lecture 1 to lecture 3, so to the memory management part, and we will not cover the advanced topics. So the advanced topics I will mark like this is advanced, like one moment. Like here, there are all advanced topics. So they will not be in your midterm. And then, and because we have a little bit too many of folks here, so like we will split you into 2 rooms. So one will be in the EC building and one will be here. So we will announce the seat table this week. And we'll also announce our second hands-on on October 28th in 2 weeks. Okay, so like the form for the midterm exam, I think you guys can find most of the resources in the internet. They'll be very similar to you can see find in the internet. Okay, so questions. All right. So let's first do some Q&A, and then we'll do some recall. Oh, one more thing is actually today's all of the contents today were not included in your midterm, but excluding the recall. I mean, recall is for last week, so it sure will be in your midterm, but for the advanced topics and then for the storage device, it will not. Okay. Okay, so Q&A. The first one is when a file packet file is mapped into virtual memory, if the file is modified, will the mapping region be automatically updated? And the answer is yes. So actually all the update will be synced with the file on the storage device. Okay, so the second one is like the relation between virtual address space and memory fragmentation. I think this is a good question. And the answer would be like, actually, the virtual address space, I mean, the design goal for the virtual address space is not going to alleviate or like remove the memory fragmentation. The virtual address space is designed for making each process has their own consistent, isolated, and flexible memory view. So it makes the programmer easier to do the programming. The programmer doesn't really need to care about the other programmers, how they use the memory. So this is virtual memory. And the thing like it can really solve the memory fragmentation would be the physical memory allocation. So it includes like patch frame, and then it includes like body systems or even like the slab allocation. They are all possible to deal with the memory fragmentations. Okay. So another question is about why MM structure only records the number of threads and process. There are detailed information about threads and process stored. So actually the detailed information about threads and process, they are stored in the text dash structure, data structure. So usually people call them PCB. Okay, so actually structure, the only records about how many kind of process and threads they are used in this mmap structure. Okay. So there is a question is about, given some cases like where accessing a VMA is illegal. So here are the 3. I mean, there are more, but I just put 3 here. So the first one is a process access outside memory boundary. So like if the process access like the kernel memory or like the process access the memory, it doesn't kind of belong to this process. They're all for the memory outside the memory boundary. So there's the second case is about a process access read-only virtual memory with the write operations. Okay, so it is kind of the permission like error here. So VMA will become illegal. And there is a third case is about a process access unallocated or free memory. So it is also illegal. Okay, so in most cases when there is illegal, then there is a patch fault usually, and then kernel will come to deal with these illegal things. Okay. So the fourth question is about in the following scenario, when we said, oh, actually these slides, they're from our last week slides. So it is on page, I think it's 23, and we are explaining about the users and counts, what's the meaning for these two fields or like the factors. And we give you an example to say like, hey, if process one has 5 threads and you have blah, blah, blah scenario. And the question is about, we say process one has 5 threads, but actually the users is 5. And the reason is because when we say process one has 5 threads, it means process one itself is 1 thread and it has 4 user threads. So the total will be 5. Okay. So process one itself is also, it will be recognized as 1 thread in Linux. Okay. So this is also the reason why I said in Linux, it doesn't really matter about it as a process, because the key difference is about the capability to access the resource, just like what kind of resource they are isolated for process, but they are shared between threads. It's much about this kind of things. And the fifth question, I think this is not a question because there are a lot of questions related to this one. So I just summarize and then do a clarification. So a VMA is mapped to non-continuous path frames via the patch table. Okay, so when we say there is a VMA region, it means like there is a continuous virtual address region there. I mean, it is comprised by a lot of continuous patch. Okay, but it doesn't mean the physical address or like the physical patch frames should be continuous, right? Because you have patch table. So for example, you have 10 pages that are continuous on the virtual memory address space, but it doesn't mean those patch be mapped to the continuous physical address. Okay, they can be mapped to non-continuous physical address. Okay, so this is also the reason why we are going to use virtual memory, because it doesn't really need to always use the physical address like in a continuous way. Okay. So the next one is in 64-bit systems, are the remaining 16 bits completely wasted? Oh, let me give you a little bit about the background about this question. Because we say like in 64-bit system, we only use 48 bits, right? So people are thinking about maybe there are 16 bits that are wasted. But I would say it doesn't really like it wasted, because come to think about, if you use those extra 16 bits to store some things, and your patch table will grow to like 5th layer or 6 layers. So each time you need to pay extra translation overhead there. So in current Linux, the reason they use 48 bits instead of more is because you can save more translation time. Okay, so because currently there's only 48 bits, so there are 4 levels. But if you increase to like 54, something like those kind of bits, then maybe you need 5 level or like 6 level. So each time when you increase 1 level, it means for most of the instruction, when the CPU is going to access the instruction, CPU needs to translate 1 more level. So probably CPU need to access memory 1 more. So from 4 times to 5 times to 6 times, then the overhead will be super huge. So this is the reason, like, actually I will not say the 16-bit is completely wasted, but also the truth is like those 16 bits are not used in current systems. Okay, I mean it is possible to be used. I mean if you code in the kernel, it is possible to store more things, but you need to pay more overhead there. Okay, so I think the 7th one is quite interesting and important. Would the number of patch table level affect TOB hit rate? So now we use 4-level patch table mapping, right? And it is possible, as I say, it is possible if you are going to use more, and then you can use like 54 bits or like 64 bits, then you will have more labels. But what's the impact for the using more labels? So actually, things like this, actually TOB is a place to cache the translation result. So if you are going to remove the overhead for traversing the patch table, then you need to store more translation resource in TOB, but the size of TOB is fixed. So you can choose to store or like to cache the translation resource of the very first level or like the very last level. Okay, so you can think about, maybe I can have one figure here is easier for you guys to understand. So like this, it is possible for you to directly store the translation for this one. Like you only store the translation resource from this like 9 bits translation to this address, and you use TOB to store it. And the good thing is actually, because this is on the first level, so in most cases, most of the address, they will have very similar, I would say that they will have the same PGD offset, right? Because from the PGD offset to the patch offsets, there are still like 27 bits here to represent different address. So if you cache the first level, then it means like for most of the translation results, you can find them in the TOB. This is a good thing. So you can increase the TOB hit. Okay, but the bad thing is you still need to work the following 3 labels. You only finish the first label translation, right? So you still need to work the next 3 labels. So there's another way is you can directly cache the last label. What I mean cache the last label is here. You can directly store the translation from this address to this address. It is also possible. Then if there is a hit in a TOB, then you don't really need to do any translation result because you already store the 4 label translation results in a TOB. But the overhead is actually there's only one possible to hit it. I mean, you need to match the full 64 bits address to do the TOB translation. So if you hit, then you can set 4 TOB work. Sorry, 4 patch table works. But if you not hit any bits here, then you need to do the patch table working. So actually, this is the decision making between like which layer you are going to store in the TOB. Given the same TOB size, you can choose to store the first level or you can choose to store the last level. Okay. And then, all right, here. So the add one will be like, will a patch fault occur while traversing a multi-level patch table? Definitely yes. The reason is multi-level patch table, in most cases, they are located there place on the DRAM, right? We need some place to store this patch table. And this patch table, in most cases, they are stored in the DRAM. But the case is like the patch table is too huge. So in most cases, we will use demand paging. I mean, like when we need one patch table and it is not in the memory, we will do a patch fault, and then the patch fault handler will move from the storage device to the memory. So they're all the same thing like when you are accessing the data. Because you can image like each patch table just like the data. Each patch table entry is just like a data, no matter it is in the memory or it is in the storage. So it just works like a patch fault that you learned before. So given some scenarios where the kernel needs to manually work patch table, this is also very good question because last week when we were talking about patch table working, I mean this one, when we were talking about this one, actually our starting point is the CPU works the patch table automatically. So when we're talking this slides, actually there is no kernel involved here. I mean, operating system kernel doesn't do anything when the CPU works the patch table, because each time CPU just access the DRAM and then do some very simple computation and then access another DRAM, I mean locations, and then get the next level, and then we access the third place in the DRAM and we get the. So it doesn't really need the help from operating system. Okay, but the case is there any examples like kernel needs to manually work the patch table? And there are some. The first of all is like adjusting mmap region. because when we're talking about mmap region, it is also virtual address, right? We need to know where is the physical address. So we need to work the patch table by the kernel. Okay, so kernel will do a lot. Actually, there are some supported kernel function that can help to work the patch table. And actually, the concept is very similar to this one. The different thing is like, actually in the kernel, you will see there's a function called pgd-offset, pud-offset here like this. So those are you can find in the kernel. There are all kernel functions. And the reason I put here is just about to that you better understand, actually there are some things happens here. But when CPU automatically does these kind of things, it doesn't really call any function here. It just finish it by the circuit. It just finished by the hardware. Okay, so you can think about the pgd-offset here. It can be implemented by hardware circuits, or you can use the software code, the C code, to implement these pgd-offset things, because they are quite easy, quite simple. They're just going to concatenate two addresses together. Okay, so the first one is adjusting memory map region, and the second one is the process creations. Because when we are going to create a process, as you know, like current system use copy on write. So for copy on write, actually we don't want to copy out the new patch table. We only copy out when the patch table is updated. But the case is how the system know the patch table is updated, right? So the kernel will first set those patch table to read only. But to set the read only flag, kernel needs to find where is the patch table. So kernel should go to work the patch table by its own, and then to set up the read only flag for those patch table related to the parent process. So in this case, after the child process created, and if someone, I mean, either the parent or the child access those patch table, then it will trigger the patch fault when they are going to write the data into the read-only patch table. Okay. And the third one, I think, is quite simple, just like changing patch protections rule. For example, if you are going to change it to the write protection or something like that, I think this is quite similar to the process creation things. Okay, just like to change the permission for those patches. Okay, so the last one is, if the base address of each of it, PGD, PUD, PND, those are all patch table, are all stored in physical address space? I would say yes, especially for the last two, PUD and PMD, they are all on the physical address space, or like they are all on the DRAM, right? But the base address of PGD, it can either be in a MM structure or in a CR3 register, because we need some way to get the PGD address, not from the patch table itself, but by like if it is placed in the CPU, then we need one register to store it, or like maybe we can put it in a data structure, because each process has their own MM structure, right? So there is a field called PGD like field, and you can get the base address from the MM structure. So actually there are two places for you to get the PGD base address. Okay, but the rest of the PUD, PMD, you can get those in the patch table. I mean, you can get those base address from the PGD's patch table. Okay, so those are the questions like I summarized out, and I think they are all kind of interesting, so I let you know here. So let's then quickly do some recalls. So last week we talked about the virtual address space, and we say like each process is given a unique and flat. And unique and flat, just like the definition is there are all here. Okay, so I'll just skip it. And then the memory address is a particular value identify a specific byte in a process address space, because now we are using the byte addressable, so the address kind of granularity will be in a byte for memory. Okay, so you can see like we use 32-bit address space, but we can represent 2 to the 32 byte, not bit, because each bit we can address in a byte label. So this is byte addressable. Okay, so this is quite important, because if there is no byte addressable, then 32-bit only can address 2 to 32 bits. Okay, so it will be quite small here. So we also give you an example. If you write a C code, it is quite simple here. Just like here is the code, and then how to map those kind of things on the virtual address space. So the top kind of 1 GB, they are all for kernel. So no matter which process, they are sharing the same top 1 GB, and they are all for the kernel. Okay, only the bottom 3 GB in the 32-bit systems, they are used by the user process. So first of all, like the text section is just like the program. So the C code will be placed in the text sections. Data section, BSS sections, they are all for global variable. The difference is initialized or not. So data section is those initialized global variable, and BSS are those uninitialized. Okay. And then we have user stack. So inside the main function, actually for the function, but for the local function, they're all be pushed into the stack. Okay. So in the main function, like you can push the variable into the stack for using them. Okay. So the second one would be like the heap, and the heap will grow from the BSS section and then to above. So the reason why the heap can grow from here is because actually global variable, when you after you program in the C code, how many global variable you can count it. I mean, they are fixed, they are static. The number of global variable will not change. So where the global variable will stop, it can be predicted by the compiler. So heap can start, I mean, the heap area can start right above the BSS sections. Okay, so heap just like the memory allocation function here. Like if you are going to have like 20 bits, something like that, then you can use a heap to grow the dynamic memory part. And the last one is a shared library. So you can imagine like if you are a programmer and you write several C codes, actually you use a same standard IO library, right? So those standard IO library, they are stored in this area. So you can also think about if there is another C code and it also uses standard IO library, then they have different virtual address space, right? Because they are different process, but they are mapped to the same physical address. They are stored in this shared library. Okay, so you only need one standard IO library in your systems, placed in some places, but you can map to several processes. I mean, all the processes that are using standard IO library, they can share this library. Okay, so this is for the virtual address space. So the next one is about the memory area structures. So it describes a single memory area over a continuous interval in a given virtual address space. So like this, actually this is the MM structure. So MM structure is just like a memory descriptor. So each process has their own memory descriptor. So inside the process, actually there are several VMA region. So for each VMA region, actually you will use one VM area structure to describe this region. So VM-area structure list is a data structure. And here is the space managed by this structure. So like this is a process virtual address space. It is like 4 GB for 32-bit systems. And like here is, you can think about maybe this is a heap, maybe this is stack, and maybe this is global memory, like those kind of things. Sorry, global variable. And this VMA is able to locate where the virtual memory is. So this is the starting point of this VMA area and the endpoint. And each VM area structure can be linked by the linked list. So they're using the VM-next to access the next one. Okay, so for the data structure wide, they're all chained together. But in the virtual address space, I mean, in terms of the space, they are not chained together. Okay. So maybe it is a little bit hard to image. So let me go back to our original process virtual address space. So this is the virtual address space that you already know, right? And then, oh, I think there's one thing is actually for heap or like for stack, no matter what it is in this virtual address space, the minimum granularity will be a patch. Okay. What I mean for minimum granularity is they're all aligned to the patch size. So the heap, if the heap grows, then each time it grows at 1, 2, or maybe 3 patch it will not be like half of the patch. Okay. So no matter which part they are, they should be aligned with the patch. So for the text section, if it is not possible to fit in one like patch area, like 4 KB, and the system should still allocate the 4 KB to these text sections. Okay, no matter it is not fit or not, we should go to give it in the multiple of the 4 KB area. Okay, so actually for the anonymous part, like heap and BSS, those kind of non-file packet things, we call them anonymous. Okay, so actually for each process, like each process, they are described by the text data structure, right? So each process has a data structure, has their own memory descriptor. And for each memory descriptor, they are going to manage several memory area structure. Okay, because like you can think about the simple thing is this is one area structure, this is another, the third one, 4, 5, and 6. So at least there are 6. Okay, so this is the most simple way. But actually, because the heap and stack will grow, and maybe the BSS section is quite huge because maybe it uses a lot of global variable. So we need this kind of data structure to manage how large it is. Okay, like this. So for the text section, actually, we are going to use the VM-start and VM-n to boundary what's the size of the text section. Is it 1 patch, 2 patches, or like if there are 4 patches? So in this case, we are going to know if how many patches they are. And then the thing is, actually, we can have several flags to differentiate different region. So actually, for the text region, we should have it for the read-only, right? Because you will not modify your code online. And because it is a text section, so it should be in an executable file. Because you are going to run this binary, so it should be executable. And we are going to get, okay, so where is the, where is the file? So the file is using this pointer to point to the path for this file. So it is stored on this /binary/execute folder, and you can go to execute it. Okay, so actually, when you are looking into the code, if I remember correctly, actually there is no this kind of, oh, this is the text section. So in this VMA area structure, there is a field coded text section. And there's a field called BSS. Actually, no, there is no this kind of description to say this is a text section, that is a stack. The reason is actually the difference between those kind of structure or like those text section, data section, those kind of things. The important thing is what is the permission? And then is there a packet file? These kind of things. I mean, Linux doesn't really need to differentiate. This is a heap, or that is a stack, or this is a text section. Okay, because with this kind of permission and with this kind of file, packet file, actually it is well enough for Linux to manage this area. Okay. So you can also think about it is because it will let you easier to understand how virtual address space look like. So people are going to give them several names about, hey, this is a stack, this is a heap. But for Linux itself, actually, it's just about a lot of logistics behind those heap and stack. Okay. So for the data section, we use the same things like the text sections. Okay. And the difference is because actually for data sections, like it can support the write. So it doesn't really need to be read only. And data section is not executable because they are old data. So they are not executable file. Okay. So this is for data section. But the thing is, because they are all initialized data, so we need to get what is the initial value. So we need to get it from the executable file. Okay, we need to get it from some place. So for the BSS, actually, it doesn't really need to be a file packet because those variables, they are not initialized in your code. So it doesn't really need to know what's the value in the code. Okay, because they are all initialized online. Okay, so here comes a like VM area structure. So this is for heap. So because heap grows dynamically, so it doesn't really know how large it is. It should be decided when you are running, and it keeps growing. So in most cases, the virtual address should not be, I mean, the height, it will be not continuous in most cases. So in this case, there will chain for a long, like for example, maybe these three, they are all related to the heap. So this is the first heap, second heap, the third heap. They're all chained together by these data structures. And then they point to different like physical address, like these kind of things. Okay. So for the memory mapping for shared library, actually it should be file backup because we are going to know where is the the shared object file. So in a Linux. And for the stack, actually the stack and the heap, it looks very similar. The different thing is for the stack, it can grow down. It should grow down. So stack function should grow down and heap will grow up. So for this tag, it will be VM-grows down to know, hey, actually this is a stack. Okay, so this is the relationship between the virtual memory area and the virtual address space you learn in the undergraduate. Okay. Okay, so hash table. So hash table, just like it is going to like a book that record the translation result between the virtual and physical. Okay. So with this hash table, you can translate the virtual address to the physical address. So it takes responsibility for address translation, and each process has their own patch table. And for all the threads, actually they share the patch tables with their parent process. Okay, so for threads, they have no patch tables. I mean, they have not their own patch table. So each patch table comprises a bunch of add byte patch table entries on 64-bit systems. And the size of patch table is proportional to the memory size. I mean, the more memory you use, the larger the patch table it is, because each 4 KB patch, usually you need one patch table entry to locate where it is. Okay. So Linux use the multi-level patch tables, and now we only use 48 bits out of the 64 bits, so there are 4 levels. So in most cases, when CPU is running the instructions, they're going to fetch your data, those kind of things. CPU should first work a patch table to get where the data is. So CPU will run, or I should say, CPU will traverse the patch table automatically. And TOB is a hardware cache to keep the mapping between the virtual and physical in the CPU. Okay. And there are two kinds of patch faults. One is minor and the other is major patch fault. And the key difference is for major patch fault, it will involve the IO movement for major patch fault. So major patch fault is the things you learn in your undergraduate. The data will be moved from the store device or like the network device, IO device to the memory. And minor patch fault, they will not involve IO movement here. So usually it is about the MMU is not really ready for serving this kind of, or I should put like this. The patch is already in the memory, but it is not marked. For example, maybe the entry is not set it. And maybe when we are using the memory allocations, and if you are going to allocate a super huge region, but your code doesn't really use that much of memory, so those memory will not be, the address translation for those memory will not be set up when you do the allocations. So it will be set up when your code access those region. So this is what I say, like once being touched by your program. So how the CPU works patch tables? I will quickly go through this because that's why we already did it twice. So this is a 64-bit systems, and actually the first few bits here, they are unused. There are 16 bits, they are unused. And there are 4 labels for PGD, PUD, PMD, and patch table. So you have 4 level patch table working. And the last one, the patch offset is for the system to locate the data inside a patch, right? Because each patch is 4 kilobyte. So if we are going to get the exact address inside the patch, we need this 12-bit. This 12-bit can address inside a patch. So you can think about PGD, PUD, PMD, and patch table. The four combined together, you can get where the patch is. And then if you are going to know more about, hey, I'm to get like the first like 1 kilobyte inside this patch, then you need to use this patch offset to get it. And the base address of the PGD is maintained in CR3. So when the CPU is going to do the translation, actually CPU will only get this one, the virtual address space here, and the register is already in the CPU. So CPU know where is the base address for the PGD. Okay. So with this base address is always point to the bottom of the first table of the patch table. Okay. So for this patch table, actually it stores in 4 kilobyte patch frames. Okay. And each PGD entry is 8 byte. So 4 kilobyte divided by 8 byte, there are 512 PGD inside. And we are going to know which PGD entry is it. So we will use this PGD offset to know where is the PGD entry that we are requiring for. And for this PGD entry, actually, we can get the next level's bottom. So this PGD entry will point to the next level, the patch upper derivative PUD table here. And you can think about like PGD entry, this one will point to another patch frame, and this patch frame is also belonging to this patch upper directory table. So for the patch upper directory table, there are more. Maybe there are 512 of the patches there. Okay. So we do the same thing because we are going to know where the entry that we are going to get. So we use a PUD offset to locate the PUD entry inside the patch. So with this PUD entry, we can get the next label, and it iterates. There are the same things, okay, until the last label. Because the last label, actually, when you read out the last label, the layout like this, we say like each entry is 8 bytes, so there are 64 bits, and the first 12 bits, actually in the last label, there will be control bits. So control bits including the present bit, dirty bits, those kind of things, there are for control bits. They are still unused. So these 16 bits, they are unused. And between the 12 bits and 48 bits here, it is the physical address. Okay. But this physical address only point to the patch. So if you are going to know the exact address inside the patch, you are going to concatenate this patch offset with this control bit. Okay. So what MMU usually do is like this. MMU will concatenate the offset to here. It will replace the first 12 bits and then do the concatenation together. So it is quite simple circuit here, just like to concatenate two things together. And you can get a 48 bits physical address. Then we are finished the translation. Okay. So this is for the patch table working. Okay. And the next question is about like why it is 4 label. I mean, is it possible to be like 3 labels, or like is it possible to go it up to 5 labels? The reason for 4 label is because the assumption in current Linux is the regular page size is 4 kilobyte. So there are 2 to the 12 bytes. And the virtual address space size is 48 bits. So we use 2 to the 48 bytes. Okay. And the patch table entry size is 8 bytes, because there are 64 bits here. So we use 8 bytes. Okay. So with this kind of stack here, it is possible to calculate how many labels that we are using. So the key thing for doing this calculation is for the first label, it should be, I mean, for all the entries belonging to the first label, it should be inside one patch. Otherwise, the PGD cannot get the right patch for you, because PGD can only point to the base address, and there's only one patch can be pointed. So the first label, for example, like this, if your first label, there are 2 patches here, then you only have 1 PGD, then you cannot get to the correct patch, right? So if your first label, there are 2 patches, you need 2 PGD best address. Or you can think about you need 2 CL3 register. So if there are 3 patches for the first label, then you need 3 CL3 registers. But current CPU, current Intel CPU or AMD CPU, ARM CPU, they only support 1 PGD best address in most cases. So the first label should be fitting 1 patch. Okay. So let's do the calculation. So we are going to calculate how many patch table entries there are. So for the last level, like we say we have 2 to the 48 virtual address space. So we divide by the 2 to the 12 patch size. And then we can know we have like 2 to the 36 patches here. So for each patch, we need 8 bytes. So the size of the patch table entry total will get 2 to the 36 times 2 to the 3, so 2 to the 39 bytes. But 2 to the 39 byte is larger than 1 patch, because our goal is to let all the patch table entries for this level to fit in only 1 patch. And 1 patch is 2 to the 12, like this, the patch size here. So 2 to the 39 is larger. So we have a lot of patches to store this amount of patch table entries, okay? So it is not possible to fit. So we need the next level, okay? So to fit all this to the next level, the calculation will be like 2 to the 39 divided by 2 to the 12, because we need to store those patch table entries inside the patch table. Sorry, inside the patches, okay? So 2 to the 39 divided by 2 to the 12, and then times 2 to the 3, because we are going to know the total amount of the patch table entries here we are going to use. So for this one, we will get 2 to the 30 byte. So it's here. This here is 2 to the 30 byte. 2 to the 30 byte is still larger than 2 to the 12 byte. So we need another label, and then you repeat. So until you get the one thing is, when you go to the fourth label, you'll find actually you will get the size for the fourth label is 2 to the 12 byte. Actually, 2 to the 12 byte is possible to fit in 1 patch. So we will stop here because it is enough. I mean, it is possible for you to say, okay, I cannot get more label, 5th label, 6th label. They're all possible to get. But the more label you get, the higher translation costs they are, because each time, each label, when CPU access, they will be on a DRAM. So each time will be 1 DRAM access. Okay. So 4 is the minimum number for this. Under this configuration, 4 is the minimum label for the patch tables. Okay, so this is like this. Okay, so actually our midterm will cover only till here. And then the next 3, I'll say like designs, I think it is quite interesting to let you know. The first one is, so we talk a lot about like there are virtual memory, those kind of things. But have you ever think about, in terms of CPU, how to enable MMU, or how to begin the memory virtualization? Because if you still remember for the kernel, when the CPU is going to do the kernel translation, actually it doesn't really need a very complex patch table. We just add an offset, then we can get where the kernel address. But when we are running a user process, each instruction, I would say maybe not each, but most of the instructions, you need to do the address translations, and it takes a lot of time. And using this translation, you will translate to different place, and usually you cannot know beforehand, right? You need to work the patch table. So actually, when the system is boot, the MMU is inactive. So it means when the system is boot, there is no patch table, okay? So MMU is active until CPU runs a specific like instruction, okay? So the instruction is to set the CP15 register to 1. Then it will put the CPU from the physical address space to the virtual address space. Before MMU is activated, CPU only execute on the virtual physical address, because CPU doesn't really know the virtual things. Okay. So like this. So this is a physical address space, and CPU will start to execute the first instruction, second instruction, as I say, right? So when CPU execute to this 0x40, this address, and CPU access this store CP15 to 1. And CP15 is the 15 core processor in Intel CPU. I mean, different kind of CPU mode will be different. Like AMD ARM, they will have different way to enable the MMU, but this is only for the CPU, the Intel CPU. So I think it is hard to image what I was saying. So I give you an example. If this is a very simple CPU and there is a cached MMU and this is a CPU, right? So enable MMU means like this. Okay. So this is an enable MMU command. So when you execute it, okay, and there is a thing called jump, because you need to think about like when you enable the MMU, then in 0x44 after this, MMU is activated. Okay. So we will use a jump command to jump to the place that where is the user program is. Okay. So because now 0x40, 0x44, they are all for like the system built-in phase. But your program, your code usually is not here. Usually they are for system built-in things. So if we are going to get where the code it is, where is your user code, we need one jump command. Okay. So with using this jump command, like this jump command 0x100 will jump to here. Okay. So because 0x100, it is also a virtual address. So using the MMU, it can be translated to the physical address. So after the translation from MMU, you can get a physical address is, hey, actually your next process is on 0x84. So the key thing is this jump command to execute your first program cannot be physical address here. It should be some virtual address. And you already know it is translated to this physical address. And then after you activate the MMU, I mean after 0x44, all of the instructions, they are virtual instructions, they are virtual memory, they are virtual address. Okay, so you should use the MMU to do the translation until CPU inactivate MMU. I mean, CPU is also possible to inactivate MMU, but at that time, what CPU see, they are all physical address. Okay, so this is quite tricky here because actually 0x100, is it a virtual address or is it a physical address? They're all possible. It depends on how CPU translate, how CPU explains this address. I mean, because here is MMU. So when you are a programmer, you should know this will be a virtual address. But I mean, if there is not MMU here, if CPU doesn't run this command and CPU directly run jump to the 0x100, then CPU will directly jump to 0x100. Okay, so in this scenario, 0x100 will be a physical address. Okay, so this is how the virtual address was the beginning of the virtual address. Okay, so the second one is about the inverted patch table. So system needs a large memory space to store multi-level patch tables, right? Because each level you need to store their patch table entry and you need to store to a lot of places. It comes to a lot of memory. So there is another patch table called inverted patch table. Maybe you already learned it in your undergraduate, but I just recall it for you. So inverted patch table usually it is a single level patch table. And a PD is quite simple. The process ID, patch number, and offset. So with this information, you can finish the inverted patch table. So like this. So process ID and patch dash number equals the function of multi-level tables. Because it directly write into their patch table entry. So if you still remember in the multi-level patch table, actually there is no process ID here because each process has their own patch table, right? So the different thing is for inverted patch table, there is no multiple level here. So it is not possible to store like for each process they have their own patch table. So all the process here they share the same patch table. But like we need some way to identify, oh, okay, this is for process 1, that is for process 2. Okay, so they share the patch table. Okay, So if a match is found, that means, okay, process 1 is going to access its first patch. Then we can get the physical patch by I offset. Oh, sorry. I think this I should be this I. That should be the same. Okay. So with this one, actually you can directly do the translation. It's quite simple. Just like you can check the first one, second one, the third one. And then if it is the fifth one, the PIDP, and then you can directly say, okay, the physical address is on the fifth location, and you can get an offset and you can write it. Okay. So this one is because all the process they share this patch table. So if you sort the physical address by if you store the physical address, then you can assign the physical address to each request. For example, process 1 is going to have to allocate this first patch, and then we will give it the first address of the physical address. And then process 2 with its first patch is going to allocate one patch, then physical address can give it the second one. And because this patch table will only go down, so each time when the process is going to get a new patch frame, we can give it in a sorted way. Okay. So this is inverted patch table. And here are several disadvantages for this design. The first one is it should walk through the whole table if there is no match. I mean, actually it doesn't really know how many process ID there are. And you also don't know how many patches are there for each process. So this table will be super huge, but it will not be larger than the multi-label because there's only one label and all the process share this label. So it should be smaller than the multi-label. But the thing is, there is no faster way to do the search. You save the memory, but you trade off for your performance. And the second one is only physical patch can, one physical patch cannot have two shared virtual address. The reason is the physical address is allocated according to those, we sort all the physical address, and if there is a request, we give the ID for the physical address out. Okay, so in this case, if there are two if there are two patches that are shared for one physical address, actually in this physical patch table, it cannot happen here. Okay, because we use the index to do the physical address tagging. So no two patches or no two process can share the same physical patch. So this is the drawback for this design. But I mean, usually for this inverted patch table, they can be used in the embedded system, because for embedded system, if there's only one process or like two processes and there are not much of patches, then this one will be super fast. I mean, it doesn't really need too much of memory. And usually for embedded, if they're not using this kind of share, like one physical patch shared by two virtual address, then it is a good fit for it. Okay. So the third one is like the huge patch. I think maybe we can tag a 10 and then come back later. Okay.
你刚刚说，如果我借了第一个层最后一层，那个 miss 的话，就是要会有3层 overhead，
没错
要从头找到嘛。如果我是存在第一层，那 miss 不是也要找3层吗？这样差
对啊，差在如果第一层的话，有很多人都可以 share 第一层的资讯。
很多人
就是你，因为他这边这9 bit 嘛，所以你后面这群人，只要前面9 bit 是一样的，都可以学这个。对，所以你后面有很多啊，你后面大概有几个 bit 啊？27个 bit， 再加上这个，所以38个 bit， 这样这一组人，先看这中间好了，这27 bit 所代表的 patch table 都可以被前面的组去做定位，所以你只要存这层，你后面这些人都可以快速转换。
找到的话，就可以比较快。
对，没错，它就可以比较快的进到下一层去。对，对。
你要写信那个想问一下，就是这边是启动，
对，
启动那个 MU，这边是跳转
跳转到
在
作用是什么？
跳转到就是因为你启动 MMU 了，所以你这个0x100，如果你直接就是因为假设你知道你的扣放在0x84好了，可是如果你这边写0x84的话，它不会到0x84，因为它会经过 MMU。对 MMU 来讲，0x84它是虚拟集体位置，它会直接对应到另外一个实体位置，所以它这段扣是一开始就先知道它的这个它是 physical， 它的 virtual 叫0x100，就是它在一开始在 bootstrap 的时候就设定好说这个人的 physical 的 virtual 是0x100，
哦，
所以它会直接跳过来。
0x100是 virtual，
对，
就是0x40的时候就直接跳到 virtual code。
对，
哦好，还有另外一个问题就是那个像问题要加分是要在线上问吗？
不用，就是你现在问或者是你在这边问，然后你就把你的那个问题写一下，然后寄信给主角就可以了。
哦，
只是说在线上问的话，你要截个图，因为我才知道到底是什么时候问的。
那所以我说我这样问这样算吗？
这样可以啊，你就直接寄信给主角说你问什么就可以了。
好，
对，
谢谢老师。就想问就是在做这个的时候，是只有一个这个，还是你进到这个里面就会有一组这个？
一组
就是
你每一个这个就代表一个这个完整的。
所以我有一开始的 base 这个，然后进到这个第一个，然后就会有一个这个，然后我想要进到下一个就看这个就好。
其实这个加号只是我把最后面这个取代掉，只是说呢，这边这一组 base 的64 bit 的，我只取代最后面9 bit 掉而已。
哦，
所以这样子一组，其实它是会直接对应到这个地方，只是我把后面的9 bit 取代掉，我就可以知道是在哪一个 PGD entry 这样子。所以这个读出来又是另外一个一模一样啊，不能说一模一样，就是格式是一样的，只是你今天去取代的是，就是也是最后面9 bit，只是你拿这个 PUD 去取代这个9 bit。对，
所以那最后这个12 bit 老师刚刚说
这12 bit是因为你要定位的是哦，为什么这9 bit 是因为你这里面是有512个 PGD entry，所以你知道9 bit 去定位这512个 PGD entry，然后这个是12 bit 是因为你里面你是4KB，所以你需要2的折四方去定位4K byte。对，
定位 page table。
没有，这个最后一层就是定位你的资料，就在这个4KB，对，要的是哪一个就是资料这样子。
好，谢谢老师。
想问说这边，
嗯，
假如它的有个发展单段修完，它就会放到100里面。
对。
然后等到这边没有一个币是1的时候，它才会交换 n 点跟 x 版。
没错。
假如有一个比较高优先权的那边，它做完，然后现在它写完放到1里面，然后这边一直有低优先权的情况。
好，这是好问题。其实这个地方它并没有考虑到高低优先权，因为它这个地方是给一般 process 去做的。但是确实如你说的一样，如果它是个高优先权的话，它应该会直接用，就是例如像 FIFO 那种，就是下一页讲的 real time 那一些的。对，就是它也可以放在里面，只是说它会有个机制让它再回去使用它。对，就是它这个只是个概念是说，如果大家优先权都是低优先权的话，那它可能这样用。但是如果它里面有高优先权的话，它就会再被 activate 回去，然后再回到这个地方来去做操作。对，谢。
之后你再去。
我想问一下，这个 minor page code 它的意思是说，就是现在 memory 里面嘛，就是 MA 有找不到这个 virtual memory
对。
对。那我能想到一个合理的情况就是这个，就是 share library 嘛，就是对，可是像其他情况，虽然他都找不到了，那为什么 MNU 可以就是很快的解决这个问题？就他居然都找不到。
就是举例来说哈，就是如果你直接跟系统要一个 memory location，你要了一个1G 好了，
对，
可是系统并不会真的给1G，因为如果每个人都要1G的话，就没记忆体了。所以系统会让你觉得好像给你1G，但其实实际上呢，这个是没有那个 MAU 去做对应的。就是你只有 virtual 是1G 的没错，但你 physical 在哪，它还没有分配给你，
它没有分配，
你要存取到的时候，它才会分配的给你。
哦，所以 Melo 它不
对啊，
不是 Meloc 它会先 map 一块给 process。
哦，我应该这样说那个 Melo 它其实是跟 library 要，然后是 library 会拿一块起来。
那
但实际上它如果还没被存取的话，那个链接不会被建起来。physical 因为 map 它是它如果是 heap 的话，它那一块连接是只有 virtual 会建起来的。
所以 map 会拿到一个 address，
对，拿到一个 virtual address
但是其实 page table 里面是还没有
的，对，
所以你要去写东西，它才会，
它就会触发 page4，然后就帮你建立起来。
帮你建立起一个 OK。
对， 它就是建立起来之后，然后如果你有，就是你需要分配机体空间的话，它就是在用 physical address location，把 Y 配起来的，不然配起来。
可是那他怎么知道这一块机体有没有被 MM 过
有没有被 MM 过？你说是 virtual 的吗？
？Page table 里面，所以 page table 里面会写说这一块其实是有了，但是还没有 MM，因为还没有 physical 这样。
对，它应该会有，但是我忘记它怎么做，但是它会有一个方法是知道说这块 MM 是illegal 的，对，
哦
因为它的 physical 可能空的，或者是它可能用某些方法去 protect 到这个。
，OK，
对对对，
所以 malloc 的情况是 virtual 直接没有对应的 physical，然后他还要去打一块新的给
抽到他就要
对，它说
然后 share library 或其他分享档案的是，他已经从 disk 放到那个 memory 里面了，只是还没有建立关系而已。
其实还有一种可能性啊，
不一定还没放，他可能不会放，他只是会先说
他如果还没放就是 major 咯，
major，
就是档案直接不在那个 memory 里面。
对，如果档案不在没有就对对对，这个其实还有一种可能性，就是你 process 在做 create 的时候，因为你 create 的时候是 copy on write，所以你那个 page table 是 copy on write 出来的，对，
所以要 write 的时候就要在
对，
也是会把
但资料本来就在机体里面，
对
资料本来就在那个，就那个 memory page 本来就在机体里面的话，它其实蛮
哦，对，那最后是这个，就是我想确定这个意思是，他今天会所有 process 都共用同一个 page table，然后今天还要就全部走一遍。
对
，OK，好，谢谢。
对，那就从我的手边。
这是一个 process，然后它会有很多 BMA 去做管理嘛。那我想问一下，那为什么它需要？为什么需要这种分开的？为什么不直接一个连续的 BMA 就好了？为什么要切成多个 BMA，然后导致中间会有？
因为
或者没有这用起来？
因为它第一个点是它的权限不一定是一样的，就是你这个权限跟这个权限不一定是一样的，所以没办法合在一起。就假设你权限都一模一样，然后你边界是碰到的话，它就会把它合在一起。
哦，所以主要是权限问题。
对啊，因为你原本确实如果还没有 DLK 的时候，它很容易把它凑成一个连续的。可是你今天如果你开始在 DLK 的时候，它就会一块一块的。那你一块一块的，如果它权限不同的话，它就没办法合在一起。可是如果它权限是一样的话，它就可以合在一起。
那这样多的不就浪费吗？还是之后还是可以塞到这里？
不要，因为这都是4KB，就是它多都说是4KB的倍数。它不会小于4KB，所以你多了就是下次如果有人分配的话，那你就是它就是这个空可能会比较小一点。它当然还有个可能性啊，就是它都完全找不到连续的空间的，因为它可能要一个比较大的空间，那它可能就是会把这边重新做 remap。对。
还有，想问一下，是刚刚这边听不太懂，就是这边最后找到地址之后是找这一块的。
对，这块是指到你要的那个 page，可是那个 page 有4KB，那你4KB里面，假设你要某一个 bit 的话，你要靠这个 offset 去拿，因为这是12 bit 的原因，就是因为我现在一个 page 是4KB，所以我需要2的4方去做内部的定制，一个 page 内部的定制。那要怎么知道内部定制是多少？就看这个 offset， 所以它其实实际上你要去戳到哪一块机体位置，它是这个加这个，就是这个 page 里面的哪一个位置。
那这上下这两个，
这个是这两个是因为你这个在 page table 里面的时候，你本来就不知道它在哪，所以你这块本来就是空的，因为你还没把它搬过来。
什么时候？
就是这里是 virtual address，所以你要给了 virtual address 之后，我才知道你要拿这个4KB 哪个地方。所以对于 page table 来讲，它只会定位到你要在哪个 page 而已。所以你只需要到12到48 bit 就可以知道哪个 page。可是你这样还有12 bit 没用嘛？那你这12 bit 就可以拿来做一些用途，例如你要去确认说这个 page 有没有在机体里面，或者是这个 page 它是不是被写过这种，所以它就是这边预留了12 bit，每个 bit 都有一个用途。它这个就没有，这就是因为它就没有别的用途了，所以它就空下来，这是空的。
之前提到 BRK 这边，它是可以去增加 BM 的 size，然后它是说是借由增加 BNN 的运作。对于像是我们讲的 user stack，它这边还有特别的一个 flag 是说它是从上往下涨。那这样的话，它还是 它这样的话，它去增加 BMA size，它
我觉得它往下涨只是把 star 跟 end 互换，这个 star 是 end，
哦，
它说它就可以往下涨。
所以说它这样的话，对于 stake 来说，它就会去把 BM 的 star 的去往下减。
没有，就是它因为它已经说它是 growth star 了，所以它的 star 应该会掉空的位置，
会掉
因为它 always 应该只会涨 BMN，会比较好实现，对吧？就是如果它每 always 只要涨 BMN 的话，那它因为这个是 growth down，所以它 M 的往下涨就可以了。
更的往下，
就是它这边没有写 growth down 的话，你看它这边是这是 star 这 N，所以它往上涨。
哦，
可是 growth down 的话，只要把 N 跟 star 的 field 把它倒过来就可以了。因为这个只是一个指标，让我们知道说它涨的方向是哪个方向。所以你可以想象它往上涨的话，那就是 M 的，就是往那边加。那往下涨的话，只是 BMM 去建一个东西而已。
所以说这边的值其实是直反过来的，是吗？
对，
还是说是对于这个，
就是这个 stake 来讲的话，你可以想象的就是 BMM 的会一直往下涨。哎，我这边好像画错了，它这个应该是不同的，不好意思，这个画错，我这应该在上面，这在下面。对，
所以是会变成说它的曲线
不好意思，对，曲线在下面，对，
它的 end 会去扣，
对。但其实你要涨 start，理论上也不会有问题的，就是因为它每次要涨 start 还是涨 end，它其实是会经过确认的。
哦，
它的核心概念只是不希望去带到其他人的地方。只是如果以基于程式码实现的话，你多涨 end 是比较简单的，就是你在写 code 的时候，我是说 kernel code 的时候，对。
所以它主要是它主要用这个东西的加法，只是去为了之后去算 overlap 的成本好算。
对，重点就是不能 overlap。至于要怎么涨，其实都会，因为也可以强制它去涨 BM star 也可以。不过呢，它这个有点顶了，所以它不能再涨 star 的。对。但是我的假设说，你今天中间这一块好了，你要涨 star 还涨 end，其实是都可以做到的。对。
所以说理论来说，这边是 end 跟 star， 然后是 end 往下，
没错，
往下减。
对，感谢。
我想问一下，其实就 CFA 是还是对那个 normal process 来的，然后real time 是另外用其他的。
对。
那他就是他一开始就是他会是先决定说他是 real time 还是 normal，然后再分配权重，还是他是先给权重，然后根据分还是 normal 还是 real time？
其实我们计划现在的理念是应该是，它会把这两个整合在一起，就是它也可以从 CF 去做到 real time 的排程，然后就像你刚才提到一样，因为它会有 nice value，所以它本来一开始就知道说你是 real time 还是你是 normal process 这样子，所以它透过这个它就可以去分配说你应该用 real time 排程还是你是要用 CFS。然后我没记错的话，现在一般的 kernel 来讲 ，CFS 它会设计的比较复杂，就是它的整个，因为这个是一个简单的示意，说 CFS 大概是长这样子，可是他没有考虑到的是，今天如果我有就是需要多个 process， 它可能是有 preemption 功能的，就它可以把别人那个踢掉的话，那我应该要怎么去做一个更好的设计？对，
所以比较像是他会先就是给他权重。
对，权重是一定会给的，因为权重就是那个 project 在 create 的时候，它就是会从你的 parent 去做继承，所以权重是多少是从继承来的。当然你可以从后天去调它，对，所以权重是本来就会有的。对。
对啊。哦，每个 parties 都有自己的 page table。那所以我是每个 parties 的 page 都传成什么？还是
再讲一次，
每个 party 都自己 page table，那就是都从一这本上。
哦，没有，就是理论上你这样讲理论上对的，可是因为它 page table 很大，所以它不太可能所有人的 page table 都存在记忆体里面，所以它其实会把没有用到的就形态存在 storage， 然后被存取到之后才会把 storage 的那个部分拿到拿到机体里面去。对，但如果你机体真的是超大的话，理论上这样做是没问题的。对，谢谢。All right, so let's come back. So let's talk about the huge patch management. So before this patch, actually, we are saying the page size is usually 4 kilobyte, but actually the page size can be larger than 4 kilobyte. And sorry. Okay, so actually the page size can be larger than 4 kilobyte, but in current Intel CPU, it only supports 4 kilobyte, 2 megabyte, and 1 gigabyte. And there is a reason. So the reason is like this. When we are saying we are going to increase the size of the patch, then we say if the page size is 4 kilobyte, then we are going to use the last 12 bits to address or to locate the data in this 4 kilobyte, right? But if I split from here, the 21 bits, so the 21 bits means 2 megabyte, right? So this is a reason why Intel supports 4 kilobyte, 2 megabyte, and 1 gigabyte. Because if we split here from 2 megabyte, so we only need to translate, we only need to traverse 3 tables, right? Because after 21 bits, they are pointing to the same patch. Then we only use this. We can use these 21 bits to address the data position inside this 2 megabyte patch. And the same thing for 1 gigabyte. So if it is 1 gigabyte patch, actually we only need 2 patch table walk. Then we can stop here. Then for these 30 bits, they represent the data inside 1 gigabyte patch. Okay, so maybe you already find out some interesting things. So when the size of the patch grows, actually it can reduce the number of patch table walk. So one of the main goals for increasing the patch size is to enjoy the benefit of fewer patch table walking. Because if you are using 1 gigabyte, then you only need to walk 2 patch table. Compared with if you are going to walk in 4 patch table, you can save like half of the time. And because virtual translation, virtual to physical memory translation, usually you need to do for most of the instructions. So it affects a lot for the CPU performance. If you can only set half of the patch table translation numbers, then you can boost like twice of the CPU like performance here. Okay, so this is the goal for this kind of huge patch management. Okay. And before talking about huge patch management, I think we need to do one thing is actually when you are using a huge patch, it doesn't only benefit the patch table translation, it also can increase the TOB reach. So here is a definition for TOB reach. TOB reach is the TOB size times the patch size. So you can think about the amount of memory accessible from the TOB. So because the TOB size is fixed, so for example, in prior Intel CPU, you can only do like 1,186, something like that, TOB entries in the CPU. So if the patch size is 4 kilobyte, so let's say if you can only do 1024 TOB entries here, then if your patch size is 4 kilobyte, then actually you can only reach out 4 megabyte of the memory patches. Okay, because one entry, one patch. So you have 1024 entries and each page size 4 kilobytes, so you can address it for 4 megabyte area. But if the same things, you have 1024 TOB, but now the page size is 2 megabyte, then you can address up to 2 gigabyte of the memory. So you will be you will largely increase the TOB reach. Okay, so it really helps for this kind of TOB reach things when you use the huge patch. And patch table work, I think, already point out these things. So let me give you an example. Actually, inside CPU, there is a TOB. And for regular TOB, you can see like a virtual address 0 point to the physical patch. Physical address 3, virtual address 1 will be translated to the PBF add like this. And this is for regular TOB. Oh, okay, it's okay. I'll show you later. Okay, so like this. The huge TOB will look like this. Virtual address 10 to 522. The reason like from 10 to 522 is because for 2 megabyte huge patch, it comprises 512 of the regular patch, right? 512 times 4 kilobyte equals 2 megabyte. So for this virtual address from 10 to 522, you can directly be mapped to physical address here. Then you can save a lot of the virtual address translation from TOB. Because if you are going to use a regular TOB to represent this, only this sentence, this line, you will need 512 of the entries here. Because here is 10 to 552, so there are 512 here. So for this, you need 512 entries in the regular TOB. Okay, so this is a good thing, but the bad thing, I think you already know, the bad thing is the virtual address and physical address should be in a continuous way. So for huge patch, the physical address should be continuous. I mean, for the 4 kilobyte, it's quite easier, but if the patch size is 2 megabyte, you need to have the 2 megabyte of a continuous physical address. It's quite difficult. I mean, for virtual address, it's quite simple because each process has their own virtual address. So you are going to find a continuous virtual address is quite easier. But because all the process share the DRAM, share the same amount of DRAM. So if you say I want a continuous 2 megabyte region, actually it's quite difficult. But if it is possible for you to do this kind of things, then you can get a lot of benefit from reducing the patch table working and then to increase the TOB reach. So you can greatly save a lot of for this kind of translation. Okay, so actually current Linux supports two kind of huge patch, I would say like promotion or like creations. The first one is using a library. So this library huge patch TOB FS, it works more like a file system. This is a library that can back application, text, data, memory allocation, and share memory with huge patches. So for example, if in the compiling time, you already know you have a lot of memory and they are used for the continuous way. For example, you have a lot of global variable and they can be stored in the physical memory continuously, then you can use this library to allocate for them. Okay, but this is not easy for a runtime. So the thing is, if you are going to do a more runtime things, there is a things called transparent huge patch, and this is also supported by Linux. So a transparent huge patch, there are two different operations. One is called huge patch promotion, and the other is called huge patch demotion. Okay. So for a huge patch promotion, it's like this, because we say, hey, we are going to do a continuous 2 megabyte area in a DRAM. So 2 megabyte means you need 512 or 4 kilobyte regular patch, right? Because 512 times 4K is 2 megabyte. Okay, so usually if the data in the memory is not continuous, and maybe if sometimes your data required by this physical address is backed in a swap area, like in a storage, then you need to do a promotion. Promotion means you need to copy out the data from the memory and then from the storage, and then to combine them together inside a 2 megabyte continuous area. So they can become a huge patch. Okay, so the overhead will be super huge if, I mean, the good thing is if you are using memory allocation and you do really use this 2 megabyte area, then you don't really need to do this kind of promotion because you can directly allocate 2 megabyte area and you put the data inside, then we're done later. But when the system runs for a relatively long time and the system is in a high memory pressure, and you are saying, hey, I'm going to create one huge patch, like 2 megabyte, then there will be a lot of data movement, including from the memory and including from a storage device. You need to move from storage device, from the memory device, and then put them together in a continuous 2 megabyte area. So you can finish this huge patch. Okay. Okay, so I think that is enough for you to know about the huge patch. So that is all for the lecture 3. So let's move on to lecture 4. So lecture 4 will not be in your midterm, but it will be in your final. Okay, so your final actually will be from lecture 1 to lecture 5. So including the midterm part. Okay, so preparing for midterm is quite important because you can use in 2 places, midterm and the final. Okay, so first of all, let's come to look at this split view for the kernel. So this is the system call interface. So above the system call is applications. So under here are several hardware device, CPU, blah, blah. And between them, there is operating system Linux kernel. So from lecture 1 to lecture 3, what we cover is from process management, memory manager, and virtual memory, all these kind of things is here. This is before midterm. And actually, we're not covered here, like how to write the device drivers and those kind of networking things. We're not covered here. So for lecture 4 and lecture 5, what we will cover is from disk to block device for file systems and then to the file system part. So we'll cover all this path out. Okay. So first of all, let's talk about memory and storage. Oh, if you guys already took the memory and storage course last week, I think lecture 3 will be highly like the same things that you learn, but will be a little bit coarse grained because you learn is more details here there. So okay, let's get started. So for the memory hierarchy, the reason like we need memory hierarchy is we're going to balance the access time and cost. So look at the pyramid on the right hand side. So the bottom is the storage and the between is memory and a cache. So actually the access time for storage is from 50 microseconds to 1 millisecond. And there is one best line is for CPU. So CPU instruction, each time it takes like 0.3 nanoseconds for a 3 gigahertz CPU. So if it is 1 gigahertz CPU, then it takes like 1 nanosecond here. Okay, so microsecond means like 1,000 nanoseconds. So millisecond is 10 to the 6 nanoseconds. Okay, so storage is super slow. And memory is a little bit faster because, oh, sorry, it's way more faster because memory is from 10 to 100 nanoseconds here. And then for the cache TOB, actually they are all SRAM based device. So their asset latency will be 1 to 10 nanoseconds. So it is around another 10 times faster than the memory. Okay. Okay, so I think the gap is quite obvious here. So the top of the pyramid is super fast, the bottom is super slow, but the price is also on the reverse way. Storage is super cheap, but cache is super expensive. Okay, so this is the reason like you do not really see someone use the CPU SRAM to that it becomes a memory. Okay, because SRAM is super expensive here. And also the density is not allowed for SRAM to let it to grow to like gigabyte level. Okay, and storage, it has better density scaling. So you will usually see currently we have like 10 gigabyte of SSD or like several terabyte of SSD. They are all possible. But for memory, you are hard to see more than 64 gigabyte. Okay, so that is for that. And there is another thing is about the capability to absorb the CPU access. So this is just a funny thing to let you know. Actually, if you have a good CPU, like patch replacement things inside a CPU, then you have a CPU cache, it can usually absorb like around 90 to 99% of the CPU access. So there's only like 10% of the memory access there are only 10% of the instruction access will go to the memory. So among this 10%, there's around 90 to 99% will be absorbed by the memory. So there are only very few of the assets will go to a storage. So there are like 10 to the -4 of the assets will go to a storage. So usually like there are only one request among the 10,000 instruction will really go to a storage. So this is also the reason why we are going to build up this hierarchy, because even we have very few CPU cache, we can absorb that much of the CPU assets. So actually it is quite effective there. Okay, so even storage device is so slow, but actually if you have a good cache and memory design, actually there are only very few instructions will really need the help from storage device. Okay, so this is the cost-effective mode for this kind of memory hierarchy. So where's operating system execution time? Because operating system execution is just about when CPU running the operating system code, like the kernel function, those kind of things, right? So operating system execution is usually between the memory and storage. So it is around like 100 nanoseconds to 10 microseconds. So it depends on what kind of code you are running. You are running context switch, you are running scheduler, or like you are only switching from the kernel to user mode to do some very simple things. So it depends. So the range is quite huge here, but actually you'll be around 100 nanoseconds to 10 microseconds here. So because running operating system takes a little bit more time. So when the CPU is getting data from memory, usually CPU will use a load store instruction to directly get the data. So when CPU uses a load store instruction to get the data from memory, usually there is no involved from operating system. It doesn't really need the help from operating system. CPU can directly get the data from the memory. Okay. But if now CPU needs to get the data from storage, the story will be a little bit different because storage device is super slow. So there is some room for the operating system to do something. So for example, if CPU doesn't want to do too long of time, then CPU needs to run context switch, right? And context switch is kind of kernel code. So it takes some overhead, like around 1 microsecond here. But the good thing is the storage device usually takes like 15 microseconds. So even it spends 1 microsecond for running the operating systems, then you can set for another 49 microseconds. Then CPU can go to do any other process. It doesn't really need to wait here for the IO completion. So those kind of patch fault handler, system call, those kind of things, they are related to the operating systems. Okay, so this is quite different for CPU to access both memory and storage. Their CPU is using different way to access the memory and storage. Okay, so actually when we talk about memory, actually there are different kind of data in memory. So roughly speaking, there are process data and file data. So the reason there are file data is because there is a thing called patch cache. So patch cache is if now you are going to read out a movie from your hard disk drive, and then if there is enough space of memory, then the movie will be cached inside the memory. So next time, maybe in a few, like 1 hour or 2 hours, you are going to access the movie again. The system doesn't need to get the movie from storage device. It can directly access from the memory, and you will get faster response time. Okay. So as we mentioned in the prior slides, CPU access the data in memory by using load store. But to be a little bit more precisely, actually, for process data, CPU access them by using load store instructions. But for file data, CPU access them by running the system call and IO stacks. Okay, so even the file data is inside the memory, CPU will do some operating system stuff to manage the data. Because if the data is in the patch cache and the patch cache, even it is a memory, CPU will run the operating system to manage them. Okay, so when we talk about load store, when CPU is going to load store data in the memory, actually, if the data is not in the memory, then memory will raise a patch fault, and usually it's a major patch fault. Then there are several things that CPU needs to do. So CPU needs to run a patch fault handler to do the fault area check-in to know, hey, why there is a patch fault. And then if CPU knows, oh, it is because the data is still in the storage device, not in the memory, then CPU will run the patch swapping. And because patch swapping takes too much of time, so CPU will run context switch to other process. So this is the flow for the process data. So if the data is in a swap area, like this path. So there is another path is about system code. So when we are going to rewrite the file, actually there's file IO, then maybe in your C code, you will write fread, right? So fread in the library, actually it will finally call the system code. So with this system code, there is another path to deal with it. So because this is a file related system code, so CPU will first check the patch cache to check about if there is a cache data already in the memory. If it is, then CPU will directly return the data required by the request. But if not, then CPU will access like the file system and then get the data to check about where the data is in the storage device. And then do the context switch. Okay. So after give you a brief introduction about how CPU access the like memory and data or like access the storage device, actually let's talk about what is data on memory storage device. So the data is a sequence of 0 and 1. For example, if there is an image, then if this is a binary image, then 0 means black, 1 means white. And if it is a grayscale, if there are 4 bits, sorry, if there are 2 bits, then 00 means a black one, and dark gray means 01, and 10 means light gray, and 11 means white. So each image can be represented by a sequence of 0 and 1. Not only images, but also the voice, the audio. So for the audio, for this signal, it can be sampled to several data points here. So if we use like 4 bits to sample for this signal, then you can see like maybe this 0111 means this peak and this 100 means this peak here. Okay. So this is how the multimedia be stored on storage device. Actually, there are still a sequence of 0 and 1. Then the thing is, but how to store this 0 and 1 in the storage device or memory device? So actually, device usually consists of material which can switch between 2 states stably. They can be memory or storage device. So the reason to switch between 2 states is because we are going to represent 0 and 1. So if one material can be switched between 0 and 1 stably, then it can represent one cell, no matter it's storage cell or memory cell. So later on, we will introduce hard disk drive and SSD. So hard disk drive, you can think about like it is about a magnetic field, like it is a parallel or anti-parallel. So it means 0 and 1. And for SSD, it means like the high voltage or low voltage. So inside the cell, if the cell is high voltage, maybe it means 1. And if it is low voltage, maybe it means 0, for example. And the same for DRAM. So DRAM using capacitor. So if the capacitor is charged, then maybe it means 1. And if it is not charged, maybe it means 0 because it is 2-stat. Okay. So there are also some new non-volatile memory like IRAM, PCM, and STT-MRAM. So all of them, they are using the switch between the resistance. So high resistance, that means like 0, and low resistance means 1. Okay, so they will use different kind of physics, chemistry, or like different kind of way to map the materials to show different high or low resistance. Okay. Okay, so we talk about like hard disk drive, SSD, they are non-volatile. And DRAM, I think you already know, it is volatile memory. So the difference between volatile and non-volatile is it possible to keep the data even when the power of the device is off? So DRAM is volatile. So when you shut down your computer, all the data on DRAM, they will get off. They will be disappear. But I mean, like hard disk drive, even you don't power for this hard disk drive, the data is still there. Even for SSD, you carry your SSD over out of the power, the data is still inside the SSD. Okay. And there is another thing is called access granularity. So it is about the minimum rewrite size of each device. So if you still remember, I say for memory, we are using a byte addressable, right? So you can see like current memory device like DRAM, like IRAM, PCM, SERAM, when they are saying they are memory device, they are byte addressable. So they can be addressed to the granularity, to the byte granularity. Okay. The thing is, actually, SSD is like patch granularity. So the minimum granularity for SSD will be like 4 kilobyte to 16 kilobyte. So it is way larger than 1 byte. So SSD is not byte addressable. Okay. So hard disk drive, like we are using a sector, and it is around 512 byte to 4 kilobyte. So it depends. Okay. Okay, so there is a comparison table between all common non-volatile memories and storage device. So first of all, is a cell size. So cell size affects a lot, because if you are a larger cell size, it means it is hard to scale down the size for this memory cell to increase the capacity. So you can see like for SRAM, the cell size is between 120 to 200 F square. And DRAM is 60 to 100 F square. But if you compare to like NAND flash, or like, oh, there's no hard disk RAM, where NAND flash is 4 to 6 F square. So you can image, actually, for the same like size of the device, NAND flash can provide you like several terabyte of the, oh, sorry, NAND flash is a SSD that you are using now. I mean, the details like how it stores the data, they're all stored in the NAND flash. So for current SSD, it is possible to offer you like several terabyte of the capacity. But for SRAM and DRAM, for one SRAM and DRAM, actually you can only get like, for SRAM it is quite smaller, like several megabytes, so large. But DRAM, it is a little bit larger. It can become several gigabyte, but still DRAM cannot achieve like terabyte level. And the reason is because the cells for this device, like SRAM cells, so what for one cells, it is around 120 to 200. So it is kind of 30 times larger than the NAND flash cells. Okay, so for these NAND flash cells, it can downsize like 30 times smaller than the SRAM cells. Okay. And the reason is because the reason is depends on what kind of the circuit things they are using. For SRAM, they are using 6 flip-flops, and the DRAM is about their capacitor, so it is hard to decrease the cell size. So there are second thing is about the write endurance. So write endurance means like when you write several times to this device, how much of the write can be endured by this device. So 10 to the 16, you can image like the SRAM can endure like 10 to the 16, more than 10 to the 16 of the assets. So it is quite a lot. But if you look at like NAND flash, IRAM, PCM, actually those kind of non-volatile device, they can only provide like 10 to the 4 to 5 for NAND flash, and 10 to the like 11 for IRAM, these kind of things. So they are vulnerable. I mean, if you write like 10 to the 6 of the amount of data into the NAND flash, then the NAND flash will be worn out. So you can think about for each NAND flash cell, it can only endure like 10 to the 4 to 10 to the 5 of the write operations. Okay, so the reason for IRAM, PCM, those kind of, and NAND flash is because they are non-volatile structure. So usually for non-volatile structure, they are going to capture like electrons, or to capture some things inside the device without power. So usually there are some materials they will there to protect those kind of data, those kind of electrons to get off. So those kind of materials, they have their lifetime. So this is a reason for like NAND flash and IRAM, they have a little bit limited lifetime compared with others. And there's another important thing is, if you still remember this one, sorry, this one. So as we mentioned, we are going to, for the CPU cache, it needs to absorb like, it is possible to absorb like 90 to 99% of the assets, right? And memory, it is a little bit lower, like there's 10% here, and then inside is 10%, memory will absorb like around 90 to 99%. So you can think about for the cache, it should have a longer lifetime because it should endure a lot of write in the cache. So if now you put your NAND flash in the cache level, and because NAND flash only have 10 to the 6 of the lifetime, so NAND flash can only endure 10 to the 6 to the assets, then NAND flash will burn out. Okay, but come back with, sorry. Okay, but come back with the SRAM. Actually, the SRAM can endure 10 to the 16 of the write. So SRAM has better capability to be as a CPU cache. Okay. So read and write latency also it differs a lot, and we only show you at a prior slide. So let me just skip this one. So power consumption, like for the leakage power part, actually because SRAM and DRAM they are volatile memory. So even there is no rewrite operations, DRAM like their capacitor will drop, the capacitor level will drop, and SRAM actually the leakage power for their 6 flip-flop, I mean the stat inside will also change even there is no rewrite operations. Okay. Okay, so for the dynamic memory part, actually we means like there is a rewrite operations. So how much energy are there for each read operation and write operations? So there's here. Okay. So I want to show you like usually for some memory they show the asymmetry energy consumptions, which means like actually if there are different states and when that's changed from one state to another state, usually that costs more energy. So rewrite, you can think about like, especially for write operations. Write operation will affect the state. So for some memory, just like SCT RAM, if it is 10 to 01 or like 00 to 11, actually it consumes different number, it consumes different energy. And also rewrite for the SCT, MRAM, those kind of memory, they consume different kind of energy to perform the read and write. Okay, so that is for the I/O performance part. So for the I/O device and I/O systems, let me give you a top-down overview about what happens here. So when the processor calls a system read or system write, so because read and write is a file-related system code, and inside the kernel, actually we'll first run a virtual file system. And then below the virtual file system, there are two paths. One is patch cache, because we are going to first check if the data in the patch cache or not. If it is, then we can return it. But if it is not, then the request will be sent to the mapping layer. So mapping layer, actually you can think about, it is the file system you know. So like ext4, beta file systems, and like those kind of different kind of like make file system, they are all in this layer. So in kernel Linux, actually you can support different file systems simultaneously. I mean, for one disk, you are going to use ext4, another disk, maybe you are going to use exFAT, those kind of things, it is also possible. So mapping there means like different kind of file system specific. And then we will come to the block IO layer. So like it will go to the block device driver, and then we'll send the request to the device. So inside the device, there are also firmware to receive the request from the block IO and block device driver there. So we will cover all from device, from device driver and IO layer, and also the file system. We will cover all of it. And for lecture, I think it's lecture 4, we will cover the bottom 3 one. And for lecture 5, we will cover the yellow part. So what you can learn from lecture 4 is about, we will introduce hard disk drive and the variant of hard disk drive called SMR, and then a NAND flash based solid state drive. And then we will talk about how device drivers work. And if I remember correctly, maybe there is a hands-on for a device driver. I think it's the third one. And we'll introduce what are device drivers and how to write a device driver. And because actually, in most cases, if you join like MediaTek, Realtek, those kind of design house company, in most cases you need to write the device drivers. So just let you know what is device driver. And block I/O layer. So we will talk about what is block I/O layer here, and maybe there is like how to merge and collect I/O operation, and what is an I/O operation, and how I/O scheduler works here. So let's first talk about the device part. So actually, you will learn two different kind of device. One is hard disk drive. So right hand side here. Left hand side here is a hard disk drive. So there are several components inside a hard disk drive. If you open the hard disk drive, you will see something like this. So there is an actuator and actuator arm. So this arm is going to read out the data, or like to write the data. So the data, they are stored on this plater. So there are several stacks of platers here. I mean, there are several stacks here, and there are several platers. So there is a spindle bundle those platers together. So actually the spindle will rotate it. And this is the reason why when you power on the hard disk drive, you hear the noisy voice. It is because the spindle is rotated. So there's a little bit noisy there. And the good thing for the hard disk drive is cheaper than SSD usually, and high reliability. Because if you store the data inside the plater, actually, if you place there, you can put the data there for a super long time. And even you write it, even you read it, there's not damage for this kind of platers. So the only things you will hurt the platers is if you drop the hard disk drive on the floor, or if you use a super strong magnetic to affect the data stored on the platers. So only those outforce will change the data stat inside the plater. Otherwise, if you normally just read and write, the life of the plater is super long. So on the other hand, for the SSD, the reason that it is called SSD, the solid state drive, is because if you look at the left-hand side again, because the spindle will rotate it, and there is a moving head here. The head will move from here to here to read out the data from the platers. So there are all moving components inside hard disk drive. But on the right-hand side, SSD, actually, there is no moving components, because there is only the controller cache and then the NAND flash memory chips here. So there is no moving parts. So this is the reason why SSD is so light, and there is no sounds when you are using the SSD, because controller just like a CPU, and they are using this kind of circuit things to read out the data from the NAND flash memory chips. Okay. So the good thing is about it has faster performance. The reason is there's no moving heads. So if each time you need to rotate the platers, you're going to move the arm to get the data, because they are all mechanical things. So it takes long time to get the data. But if most of the things you can get by circuits, I mean, you choose the voltage value, and then you send the voltage value, and then you read the current. Actually, it will be way faster than the mechanical moving part. And there is no vibrations or noise. So it is because there is no moving part inside. Lighter, smaller, and support random access better. So the reason is, if you look at the left-hand side, if the data is stored on the platers, so if you are going to do the sequential access, it is easier to do. But if you are going to do the random access, then you're going to move the arm from here to there to there to there. So you need to wait for the plater to rotate to the right position, and then you need to move the arm to the right position to serve for this kind of random access. So it takes a lot of time for hard disk drive to do the random access. But SSD, actually, it can support good random access. Okay, so I think after our midterm, we will start from introducing the hard disk drive. So thank you so much. See you guys in 2 weeks. The difference of the two context switching backboard are the difference about page flow. Okay. 听说事前说的是 Q8吗？是 Q8那问题吗？等我一下。
现在可以问问题。
哦，等我一下。好，你先问好了，你先问，我等下。
这个 V runtime 这个东西，它就只是拿来判断那个 frame 的优先度的，还是它还有其他的作用？
还有，你要这样也是可以，但是因为它 V runtime 会改变，就随着它运行的时候 V runtime 会变多，会变少，会消耗掉。对，所以当然它最后的目的是拿来做它判断说到底它要先 schedule 哪一个 process。对，
因为他想写 runtime 就会觉得说它是一个执行时间，可是它其实是经过
对，它经过时间，对，没错。你要说它执行也可以啊，就是它执行过这么多时间这样子。
可是它有经过这些权重的处理，
对，
感觉不太像是真正的时间。
它是真正时间做一个标准化之后得到的相对时间。
所以它的最主要的目的是
拿来
做那个判断要
不要判断它还有多少时间可以用，这样说。只是这个时间不是对应到真实的时间，它是个相对，就是你跟其他 project 比，如果你比较短的话，代表你比较需要，所以你就先跑。对，这个应该有一个新的 slide， 我有点忘了，反正它这个有个最新的 slide 是有一个 example 这样子，还是就这个？
应该这就是最新。
对，所以它其实会有一个，就是去判断说，你现在 virtual 如果都比其他人还要短的话，那你就可以先跑。因为你急需 CPU 这样子。
好，那我最主要只是问是不是这个目的。
OK，
谢谢。
谢谢。好。
想问的是 CPU 是怎么知道 page fault 或是 minor 还是 major？
有一个比较简单的判断就是说，因为 major 通常它在 page table entry 里面的那个 control bit，它的 bit 值会被设起来，说资料可能是在 storage bytes， 所以它会有一个 major page fault。对，通常是透过这样判断是 major， 那其他的基本上就是，大部分基本上都要先经过 minor 的处理，这样。
所以一定会经过 minor。
对，基本上都会经过 minor 的处理。对。
是可以问你一下，就是功课问题。就是
这样。不同 page size 是可以混用的，只是说在 page table work 的时候，它会先去判断你 TOB 里面有没有人，所以通常 TOB 里面它会分开来说，你是4KB 跟2 MB 不会 overlap 的。对。然后如果没有的话，你在 page table work 的时候，因为2 MB 跟4K 的差别其实只是在有没有最后一层的转换而已，因为它还是要走过 page table， 只是说2 MB 就不用走到最后一层去。对。这样，所以通常如果要实现的话，通常可能会需要另外一张 table 来去实现2 MB 的部分。对，但这个就要看系统怎么去实现它。对。
这样问一下，现在可以了哈。
OK。
那个 RAM disk 这种设备，那按照我们刚刚的分类，它应该是被分在 storage 里面，还是被分在 DRAM 里面？
我觉得它更像是 storage 那一块的，
就是没有 persistent 的 storage 对吧？
对，没有 persistent storage。对。
OK。这个提问现在是用 WebEx 来提对吧？
对。对。
其实这就是
我的那个，它后面好像说是一个 dirty 的东西，那这样是，
这是作业吗？
对对对，
还是你要不要直接问助教？
就在说，
那个蓝色衣服那个，现在站起来那个。对。
好，谢谢。
想问一下，
嗯，
还是有点不太懂，就是 hash frame 跟就是我想问，就是 hash table 里面是有很多 edges。
hash table 里面有很多 hash table entry，是这样吗？哦，就是hash table 里面它其实是更像是它会有就是每一个的8 byte 的 entry，然后hash table 4K，所以你总共会有512个 entry 这样子。然后 hash table 是存在 DRAM 上面的，所以你可以想象成一个 DRAM page frame，然后它可能就每个 page frame 可能都存512个8 byte 的 entry。然后每个 entry 是64bit，所以它会这边，就它会像这样子，每个 entry 就长这样子。只是说它这边在做转换的时候，如果它走到最后一个的话，它这边最后会预留12bit，因为它最后一个是要判断我在4KB 的这个 page 里面的我要的资料是在哪个地方，所以最后一层它会这边是12bit，然后前面这一层呢都长很类似，只是说最后面前面这一层呢，它是这边是9bit。因为9bit是因为它一个 page 里面它的 entry 大小是8 byte，所以它只需要知道这512个8 byte 它要拿哪一个而已。所以其实前面层比较简单，因为前面层就是去定位说这个 page 里面这512个 page entry 是谁。对，这样有？还是我们出去外面，我大概仔细讲一下好了，因为下一堂课老师来了。好，如果你们线上如果要问问题的话，可以直接寄信给我好了，因为下一堂课老师来了。